Hydraulic response due to a 1 meter by 5 meter channel within a permeable silty soil medium. This problem consists on the behavior and response of the soil-water components due to a channel functioning as a pumping water well. First of all, we are going to select Cut Bright from the Data Problem tab menu. Then we're going to define the geometry of the problem. The geometry is composed by a square planar surface representing the silt deposit with a 1 meter width by 5 meter depth channel in the middle of such surface, on which initial conditions, materials and mesh will be assigned. A lateral permeable soil is also included in the geometry. This is useful to ensure an initial hydrostatic boundary condition on the right and left boundary. To create the geometry, go to Geometry, Create Straight Line. Now I'm going to insert the coordinates of each point. Don't forget to click on the Join option whenever you close a perimeter, and you can skip this part. Now we have finished the geometry. Select Zoom Frame to have a full view of the geometry, and right-click on the graphical area, label All-in Line in order to label the lines in the geometry. To define the geometries of the problem, go to Geometry, Create Nerve Surface by Contour, or click on the Create Nerve Surface icon and select all the lines composing the silty soil medium, including the channel. Then press Escape and the surface is generated. The surface generated is represented by a fuchsia square. Now repeat the same for the left and right permeable soil. To visualize the information of a geometry entity, select Utilities, List Lines in this case, and select the line you are interested in. Press Escape, and a List Entities window with the information of the entity will appear. Now click Close, and it's a good time to save the work. Click on the Save icon, enter the file name, and click Save. Okay, let's define the attributes and conditions now. Let's start with the problem data. Go to Data, Problem Data, Problem Data. In the General Data tab, click on appropriate title for the problem. For example, hydraulic. Choose Full Execution from the Execution drop-down menu. Choose No Backup from the Backup drop-down menu. Choose No in the Axis Symmetry drop-down menu, and left the default values on the gravity component fields. Click Accept to save the changes. Now select the Equation Solve tab. Check the box beside Mass Balance of Water. Set 0 in the Constant PG box, and click Accept to save the changes. Now select the Solution Strategy tab. Type 1 on the Epsilon field, 1 on the Theta field. Type 0 on the Time Step Control edit box. 10 on the max number of iterations per time step. Select Direct LU plus Back 3 from the Solver type drop-down menu. Use the default option Average Nodal Degrees of Saturation, and use the value 1 exponential minus 6 for max abs PL, 1 exponential minus 10 for max null water mass val, and type 1 for PL iter core edit box. Use the default option on nodal correction or residual for the convergence criterion, and click Accept to modify the mentioned data values. Now select the Output tab and select All from the right numerical process information. Type 1 on the writing frequency edit box. Select All from the right boundary flows in additional file drop-down menu. Select Gauss points from the output points drop-down menu, and click Accept to modify the changes. The Select Outputs tab is not necessary for this type of problem. Now go to Data, Materials in order to define material properties. The Materials window appears, and now we can modify and create the corresponding material for each surface and assign it to the corresponding geometry. I'm going to modify the parameters for every material now. You can skip this part. You can use the draw button all materials to verify that you have assigned all the materials correctly. Here we see everything is alright. So click finish and let's assign the conditions. You can unassign a material from an entity using the unassign button. Select data conditions. In order to assign the conditions, there are three types of conditions for this simulation: flux VC, boundary flow rate, initial unknowns, and initial porosity. Conditions include all the properties excluding materials which can be assigned in the geometrical entities. For example, points, lines, surface, or volumes. The main types of conditions are force displacement boundary conditions, flux boundary conditions, initial unknowns, initial porosity, and initial stresses. To define the flux VC conditions, click on the line icon, select flux VC from the drop-down menu, select boundary flow rate from the flow rate drop-down menu. Now type 0.481 on prescribed liquid pressure edit box. This corresponds to the uniform water pressure along the geometry's bottom boundary, which has been calculated multiplying the saturated soil depth 49 meters by the water unit weight 9.91 kilonewtons per cubic meter. Now type 1 exponential 5 for gamma for liquid edit box. This is a constant that allows prescribing a pressure with more or less strength, and label the default values. Now click the Assign button and select lines 8, 9, and 12 that correspond to the geometry's lower boundary. Click Finish. Once selected, a message indicating that the condition has been assigned to the lines appears in the message box, and you can use the draw button to visualize the condition applied. Here we see the three lines with the condition applied. Click Finish. You can always unassign a condition using the Unassign button. Now click Close. To define the initial unknowns, click Data, Conditions. Hydrostatic initial liquid pressure distribution will be assigned on the soil surface, silty soil and lateral permeable soil, taking into account that the water level is 1 meter below the ground surface. Select the surface icon, then choose the option Initial Unknowns. Select Lineal from the Distribution drop-down menu and type 0.481 on the PL edit box. This corresponds to the liquid pressure along the geometry's bottom boundary. Type minus 0.01 on the PL final point edit box. This corresponds to the liquid pressure along the geometry's top boundary. Type 0 on X initial point and Y initial point edit boxes, and 0 on the X final point and 50 on the Y final point edit box. Click on the Assign button and select surface 1, 2, and 3. Then click Finish and draw the conditions to verify that have been applied. Alright, now we see everything is okay. Click close. You can unassign a condition as always using the unassign button. Now choose initial unknowns from the entities drop down menu. The initial unknowns window will appear, summarizing all the initial unknowns assigned. For each surface we see the parameters we have assigned before. Now click close and let's define the initial porosity. Select the surface icon that's already selected. Select initial porosity from the drop down menu. Type 0.3 on the porosity edit box. This value corresponds to the initial porosity of the silty soil. Click assign and select surface number 1. This is the big one, the silty soil. Click finish. The message appears in the message box, and now type 0.9. That corresponds for the initial porosity of the lateral permeable soil. Click the send button and select surfaces number 2 and 3. Click finish. Again a message appears on the message box. Now you can use the draw option to verify the initial porosity assigned. You can always unassign a condition using the unassign button, and if you click on draw colors you will see the conditions assigned in different colors. So now let's find the flux BC conditions. In this simulation the channel represents the origin of the water's outflow through the bottom channel line. To add this condition on the channel geometry, you must first create a new interval data. Select Data, Interval Data, click on New, click Yes to copy the conditions entered in the interval 1. Click the Open Other Data icon and select Conditions from the drop-down menu. Now select the line icon, choose Flux BC from the drop-down menu, select Boundary Flow Rate from the Flow Rate drop-down menu, type 0 on Prescribed Liquid Pressure, and 1 exponential 5 on Gamma for Liquid edit box. Click the Assign button and select line 4, that is the horizontal line of the channel. Once selected, click Finish, and let's find the flux BC conditions for the channel's lateral boundaries. The line icon is already selected. The flux BC from the drop-down menu 2. So the boundary flow rate from the flow rate drop-down menu. So now let's edit the edit boxes. On the Gamma for Liquid box, type -1 exponential 5. This negative value means that the seepage is permitted on channel's lateral boundaries. Leave all the other values as default, click Assign, and select lines 3 and 5 that are the lateral boundaries of the channel. Click Finish, and a message assigned to new lines to condition line flux VC appears in the message box. Now we're going to define the interval data. In simulations where transitory problems may occur or changes of boundary conditions take place with time, it's necessary to define several time intervals. In this particular problem, we have defined two intervals which comprise all the data entered until now, including the defined problem data, material, and conditions. Now select data, interval data, select the interval data 1, select days from the units of time discretization drop-down menu, type 0 on the initial time start period edit box, type 100 on the final time end period edit box, and leave the other boxes by default 0. Click accept. The message interval data modified appears blinking on top of the accept button. Now select the interval data number 2. Select days from the units of time discretization drop-down menu. Type 100 on the initial time edit box, 200 on the final time and period edit box, 0.1 on the initial time step edit box, and leave the other boxes with the default values of 0. Click accept and then close, and let's generate the mesh. Mesh generation consists in discretize the geometry into nodes and elements. Conditions and materials assigned to the geometrical entities are transferred during this process to the nodes and elements. In this example, we're going to use an unstructured mesh, which is composed by triangular linear elements. The mesh transition is controlled by the size ratio between adjacent elements of different size. In order to modify the value for the size ratio, select Utilities, Preferences, select Meshing, here Preferences. Now select Meshing from the tab menu, and in the unstructured size transition box, verify that the corresponding value is 0.3. If not, move it until the bar reaches 0.3, then click accept and close. Mesh density can be adjusted by controlling the element size at different parts of the geometry. The parameter which controls the triangular element size is the average length of its sides. This parameter can be defined over each geometrical entity of the problem. For this example, let's assign an element size value of 0.2 meters for the lines which compose the channel, and a value of 3 meters for the silty soil medium, and 1 meter for the lateral permeable soil. So choose Mesh Unstructured, assign size on line, and then enter size to assign two lines dialog window appears. Type 0.2 on the edit box, and this value will be assigned over the lines 3, 4, and 5 composing the channel. Let's select the mentioned lines. Once selected, the lines turn into red. Press escape. The same windows appear, and click close. Here we can see the message in the message box. Now, for the lateral permeable soil, select Mesh and Structure assign size on surface. The enter size to assign to surface window appears. Type 1 on the edit box. This is the value of 1 meter that will be assigned over the lateral permeable soils. These are surfaces 2 and 3. Once selected, press escape, and the same window will appear. And now let's assign the value of 3 meters to the surface 1, that is the silty soil surface. So type 3 on the edit box and click assign. Select surface number 1, press escape, and now close. Now it's time to generate the mesh. So go to the mesh drop down menu and select generate mesh. A window asking for the size of the elements to be generated appears. Type 3 and click OK. Now a dialog window displaying mesh information will appear, and click View Mesh to view the generated mesh. Note how the mesh generated on the channel and the lateral permeable soil surfaces are more concentrated than the mesh on the silty soil surface. You can view the enumeration of the elements of the mesh by selecting View, Label, All. And you can erase the enumeration by selecting View, Label, Off. So now to process data calculation, choose Calculate, Calculate. You can display the process information while calculating by selecting Calculate, View Process Info. Here you have a detailed view of the process. Now the process has finished. Click on OK. You can view the information of the process. Close the window. And to access the post-process interface, select the toggle icon between the pre and post-process. The post-process interface contains many features, but here I will present only some of the most common features. To display the flow vectors, select Window, View Results. The representation of these vectors is very helpful in order to visualize the flow direction towards the channel. Select Display Vectors from the View drop-down menu and click on Liquid Flow QL, and then select QL and apply. Note how the vectors, the flow seem orientated toward the channel caused by the imposed pressure gradient at the bottom part of the channel. You can change the graphic scale from here. Every time you change the graphic scale, you need to click the apply button so the vectors change the scale and you can visualize them better. This result corresponds to the time interval number 2 at 200 days, as indicated in the step drop-down menu. You can select the step you are interested in and view the results of it. Every time you change the step, you have to click apply to visualize the new graph. You can also change the color of the flow vectors to a color you are more comfortable with. To do that, select the Options menu, Vectors, and change color Mono. A new window appears. Select the color you are interested in and click OK. Let's display the liquid pressure. This representation is very useful to visualize the decay of the piezometric level toward the channel. Select Contour Fill from the View drop-down menu and click on Liquid Pressure option. Click Apply. Here you can visualize the liquid pressure. Note that the minimum and the maximum values for the liquid pressure appears on the message box. This graph corresponds to a step of 200 days. You can change the time step from the step drop-down menu. In order to observe the line of zero liquid pressure, select Options, Contour, Define Limits, and a Contour Limits dialog window will appear. Here type 0 as the mean value and click Apply. Note how only positive values of liquid pressure are drawn and represent the saturated material. It's observed the drop of the piezometric level towards the channel, which acts as a seepage boundary. Away from the channel, the initial hydrostatic level is kept. Now, to plot the unsaturated zone, select Reset Limit Values from the Options Contour. Select Define Limits, the same window will appear, and type 0 as the max value. Click Apply, and note that only negative values of the liquid pressure are drawn. This represents the unsaturated zone, the soil with air in the pores, and is located between the ground and the phreatic level. To return to the original graph, you can select Reset limit values as before, and you will see the original graph. To display a time variation of the liquid pressure, select Window, View Graph. Now select the Create tab. Select Point Evolution from the View drop-down menu and click on Liquid Pressure. Click Apply, and in the message box you need to enter the coordinates of the points you are interested in. Here you see the message. So let's enter 25.5, 50. This point is located at the top of the channel, right boundary. Then type 25.5, 49, enter. Type 25.5, 47, enter. And the last point is 25.5, 45, enter. And now press Escape, and the graph will be generated. Here you can visualize the evolution of the liquid pressure in time at different points located at the right channel boundary. Time in days is plotted at the x-axis, while liquid pressure is plotted at the y-axis. You can observe that in the time interval from 0 to 100 days, hydrostatic liquid pressure values remains almost constant in each of the 4 points. However, in the time interval from 100 to 200 days, a gradual drop of the liquid pressure below the atmospheric pressure is observed due to the seepage boundary imposed at the channel. In all points, a stationary condition is reached. This is the end of this tutorial. To exit the program, press File, Quit.